All right, so we want to take a look at ionic bonding, but first I want to mention the idea of electronegativity. I want to bring that back to us. Can somebody remind me what that term means? Electronegativity.
Isn't that like basically the attraction of like electrons and like giving or taking or something like that?
Yeah, and let's be very specific. It's the attraction of, so is that going to be how likely something is to get or to get rid of electrons if it's the attraction to get, right? So remember that electronegativity is the tendency of an atom to gain electrons. It's an index, which means it's a unitless measure. But generally speaking, electronegativity is how electron hungry an atom is. That's obviously not a technical term. That's just sort of anthropomorphizing this. Hello, thank you. And remind me of the trend. Where on the periodic table are we finding the things that are most electronegative? Where are we finding the things that are least electronegative on the periodic table?
I think those ones are more electronic, or that one's negative and that one's positive, I think. Those ones are big.
I gotta be honest, I can't see where you're pointing. But
that's negative, that's positive.
Well, what you actually said previously, you said if you go to the left and down, they get bigger, right? And if you go up and to the right, they get smaller.
Yeah.
So then think, the whole thing that makes something electronegative is that the electrons are being attracted to what part of the atom? Yeah, which are in the nucleus. So the smaller the atom, the closer that valence shell is to the nucleus. So the smaller the atom, the more electronegative they're going to be, the more attractive they are. So where's that on the periodic table? Bottom left or top right? Top right. Good. Fluorine, chlorine, oxygen, nitrogen, bromine, iodine, sulfur. Those are highly electronegative. You'll notice I didn't mention helium, neon, argon, krypton, xenon, radon. Why? They're full. So they're not electronegative at all, right? They have very low electronegativity because they've already got full shells. Very good. Very, very good. So as a rule of thumb, the nonmetals which is the right side of the periodic table, are highly electronegative. The metals which is the middle and left of the periodic table, have low electronegativity. That's the worst S anyone in the history of humanity has ever drawn. That one's better. So because everything on the right, all the nonmetals are highly electronegative, they are going to be attracting electrons, and everything on the left, which is lowly electronegative, isn't going to be attracting them. So the tendency is going to be for the metals to lose electrons and for the nonmetals to gain them. Does that make sense? Everything, if you look at that dividing line, right, everything to the left of that dividing line is going to tend to give away electrons. Everything on the right of that dividing line, they'll share with each other, but if they're working with anything on the left of the line, they are going to take them. Yes? Yep, I have no idea where it is. Who handed them out? I just said demote. Who handed them out? Are they on my desk?
Yeah.
Yeah, Nisha, they're on my desk. Good. Now, like we said the other day, atoms will only lose or gain enough electrons So atoms will lose or gain electrons to form stable orbitals. And usually that means full or empty. There are exceptions. The middle of the periodic table gets weird. Those orbitals are so big that there's different ways to make them stable. But for the most part, it means we're talking about full or empty shells. And does anyone remember the word we use for the outer shell? We're going to say that usually we will gain or lose electrons until we get full or empty. It is the valence shell. Very good. So nonmetals are looking to fill up their orbitals, right? And the metals are looking to empty their orbitals, as a rule. Again, we're talking kind of at the edges of the periodic table here. The middle of the periodic table is going to behave kind of strangely. It's unpredictable. So there's a chart below that has the charges listed, and that's all well and good, but you shouldn't really need that. You should be able to, I keep stressing the idea that the periodic table is like a map, and that it's a visual aid. And if you look at the visual aid, and you guys have been doing really good with this, so you guys the other day were doing a great job just looking at the table and using it to tell me how many covalent bonds the nonmetals would make. This is losing myself completely over here. So for example, chlorine, how many electrons does it have to gain to get a full shell? Just one. What about nitrogen? 3. Good. What about silicon? Okay. On the other hand, again, the middle of the table is going to be weird. We're going to kind of ignore it for now. The calcium, how many electrons is it going to have to lose to empty its valence shell? If it only lost 1, it would still have 1 left in. We want to empty it right out. So it's going to have to lose 2. Calcium's going to tend to lose 2 electrons. What about aluminum? For it to empty its shell right out. 3. What about beryllium? What about strontium? Rubidium? You see what I mean? Like, we don't have to look at the numbers. There's no math to do. We can just look at their location on the table, and it's telling us the charge it's going to take. Now again, in the middle of the table, they're not actually going to fully empty their shells. See how big the orbitals are by the time we get to the middle of the table? They can hold as many as 18 electrons. There's actually a few different ways to make that stable. So the middle of the table behaves a little bit more strangely. But for anything on the left of the table or the right side of the table, it's quick just to figure out. So I've given you this table, but if you look at this table, what it shows you is that the noble gases, they tend to take a charge of 0, which is just a fancy way of saying they don't give up electrons and they don't take electrons. They have full shells to begin with. But fluorine, chlorine, bromine, and iodine, these tend to gain 1 electron. And obviously I could go on and say everything here, they tend to gain how many electrons? 2. And everything here tends to gain how many electrons? 3. I'm not going to bother writing that because I think it's redundant. I think we get the idea. But if that is what's happening there, what's happening over here? Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. they don't tend to gain an electron. They tend to lose one electron. To empty their shell. Okay, if we are gaining, why do we say that's negative? And if we're losing, why do we say that's positive? That seems counterintuitive. Am I missing something? You know what I mean? Like when we say, okay, they lose an electron, so now they're negative 1. Or now they're positive 1. And then they gain an electron, so now they're positive 1. That feels weird, yeah. Yeah. Which, by the way, that's a real failure in naming. Like if you went back in time and you just said that we're calling the charge on electrons positive and the charge on the nucleus negative, all of this stuff would actually be a lot more intuitive because the things that move are the electrons, which we call the negative charges. So it's the fact that you're always moving negative charges means that every time we gain something, the charge actually goes down. And every time we lose electrons, the charge actually goes... You see what I'm saying? Like it's weird. It's counterintuitive. Sorry? Because things aren't discovered all at once and then we name them. Things are discovered as we go. So electricity was discovered before we knew how electricity worked a bit. Like we could make electricity happen before we knew why it worked, before we knew about electrons and things like that. And so we had already labeled the side of certain types of voltaic cells and stuff. This side we call the positive, that side we call the negative, such that when we discovered the electron, the charge it had was the charge that we were already calling negative. So it's just what it is. Things are discovered in order.
So nobody just didn't want to change it. It was already what it is. So
Well, you got to think, like you're already selling things, you've already got textbooks, you've already got books, you've already taught people things in school. Famously, what country was it? Oh, I want to say it was Denmark. There was a country that in the 70s, they used to drive on the left side of the road. We, of course, drive on the right side of the road. What other countries drive on the left side of the road? The UK, Ireland, Japan, I think, maybe did at one point, Hong Kong. I don't even know if they still do, but a handful of countries, but most drive on the right. Well, Denmark drove on the left. The thing about that is they have to be totally different cars, right? Like if you go to Britain, the driver's side is on the other side of the car. It's really weird. You drive there, especially if you're driving standard. Like I rented a car when we were in Ireland, and I was driving manual, and like I'm used to driving stick shift, but all of a sudden I had to do that with my left hand, right? It was weird, right? You're on the other side of the car, you're shifting, and then you've got to remember, like, you know, not to accidentally make a sharp right turn and like kill a pedestrian, which you don't want to do, right? But in Denmark, they decided that they'd be able to get much cheaper cars and many more cars if they drove on the same side as the rest of Europe. So they decided, we're going to change. But think about what that means. Like you have to change, you have to turn around every sign in the country, and you have to you have to, and people have to teach. So for like 2 years, they said on such and such a date, we're doing it. Like this is the day, you have to be ready. And there were TV campaigns about it and ads and radio jingles and things like that and billboards. And then one day everybody woke up and they had to go drive on the opposite side to what they were used to. Can you imagine how weird that would be? It'd be such a strange thing, right? And they were curious, like, was there going to be way more traffic accidents and way more things like that on that day? And interestingly, there were way fewer. And I think it's probably because everyone was driving really nervously and carefully, right? Like, if you can imagine being like, okay, like, imagine if tomorrow you woke up and you're like, all right, I'm just going to go on what used to be the off-ramp from the 406, and I'm going to drive, right, like, on the other side of it. And I'm going to trust that no truck's going to come drive over me and kill me. Like, I don't know. It would be very, very intimidating. So the answer to your question is it's just how it is. So you can come look at this table if you want. It's fine. It's here. It's in your notes. But I'm going to suggest to you that you're not going to need to once we get doing this because it makes sense. Everything on the left side of the periodic table, all the metals, they have low electronegativity. They're not going to take electrons. They're going to give them up. Right? They are closer to being empty than they are to being full. Everything on the right side of the periodic table is closer to being full than it is to being empty, so they are going to gain. Does that make sense? It makes sense. There's a logic to it. So, let's look at that. The ionic bond. With all that in mind, we're going to use an example of sodium and chlorine. Now, I'm going to ask you to draw Lewis structures. Remind me what a Lewis structure is, if you don't recall. Yeah. Mm-hmm. Yeah. If you want practice, if you don't remember doing this, because it's been a while, you could come here and do some practice. I've got a thing here. But this wants us to make a Lewis structure for fluorine. So fluorine, and then it's only the electrons in its outer shell. How many electrons does fluorine have in its outer shell? Yeah, 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. There we are. And beautiful, right? What about phosphorus? How many does it have in its outer shell? One, 2, 3, 4, 5. Yep. So 1, 2, 3, 4, 5. By convention, you put 1 in every kind of place before you put 2 in any. That sort of, you'll learn next year why we do it that way. But for now, just trust that we should. And there it is. Yeah. So with that in mind, with that in mind, we're going to use the most common example, which is just table salt. Does anyone remember what table salt is? Sodium and chlorine. Very good. So we will look at, basically, if you add sodium and chlorine together, if you bond them together, make them stick together, you will get a compound that we call, does anyone remember what we call the compound of them? Sodium. I mean, you're right, but sodium chloride. But that's okay, we'll draw it. So now let's look. How does this work? Well, sodium has what chemical symbol? Na. And how many electrons does sodium have in its outer shell? Take a look at the table. 1. Good. I'm going to use a bit of color coding here so we can kind of keep track of these. So sodium's got its 1 electron there. And over here we have chlorine. And how many electrons did we just say it has in its outer shell? 7. 1, 2, 3, 4, 5. I broke my own rule there, but that's okay. 7. There we go. Now, this should actually look pretty obvious. In this situation, which one is more electronegative? Which one has a greater pull on electrons? Sodium or chlorine? Chlorine, by far. So when these two bump into each other, hey, how you doing? What's going to happen? I got to be honest, I have a bit of a ringing in my ears and I can't hear the thing you said, but I'm going to assume that what you said, and tell me if I'm wrong, is that sodium's going to give its electron to chlorine. Great, beautiful. That's exactly right. Sodium is going to lose that electron, chlorine is going to gain it, which means once this reaction has happened, sodium's going to be over here, and it's now not going to have any electrons in its outer shell. Now, does that mean it doesn't have any electrons at all? No, because we know, how many shells did sodium have? Look at its position on the periodic table. 3, good. And the first one was full with 2 electrons, and the second one was full with 1, 2, 3, 4, 5, 6, 7, 8. So those are all still there. The only electrons lost is that outer one. But even still, it lost an electron. If you lose a negative thing, what's true? You become positive. And the way we show that in Lewis diagrams is anything that has a charge, we draw square brackets around, and we write the charge up above. With positive 1, you can just write positive, or you can write positive 1 if you like, or you can write 1 positive if you like. All are acceptable forms. I tend to write the charge and then the number, just like that. Okay. What does chlorine look like now? Chlorine now has how many electrons? Now, of course, the colors don't mean anything. I'm just doing that to show where they came from. Chlorine has 1 more electron now, and it got that electron from sodium. But if it has 1 more electron than it had when it was neutral, if you get a negative thing, you become negative. Okay. So Oh, golly. Golly gee gosh. Okay. So there we go. -1. And, yeah. It absolutely does. You're totally right. Because as we empty that out, the previous shell is full. So you're totally right. But by convention, the way we show it is we compare it to the valence shell it started with. So the truth is that it does have a full outer shell, and then that other shell that used to have 1 electron in it, it's gone now, right? Like there's nothing in it. So you're totally right, but the way we show it is this way. We show it as empty. That was a good question, though. Yes? Did I put C? This is where, guys, I'm going to say, like, oh, I was just checking to make sure you're paying attention.
I wrote it right.
Yeah, me too.
Good for you. See, I'm just checking to make... I wasn't just checking. I just screwed up.
Sassy. Oh my god, good for you.
No, I didn't mean it sassily. Really, good for you.
That's the word for today, sassy.
Sassily is a good word. Now, sodium chloride, though, isn't sodium floating around, chlorine floating around. These things are now... They're bonded. They're stuck to each other. Why? Why are they bonded? Why are they stuck to each other? It's actually a really strong bond. Yeah. Very good. One has a positive charge, one has a negative charge. And what do we know about things with opposite charges? Opposite charges attract. And it's a strong force of attraction. So these are now stuck together because of their opposite charges. That's a very strong bond. It's a much stronger bond than the covalent bond we learned about in the previous lesson. Ionic compounds are held together much more strongly than covalent compounds are. You know this because, say, what salt makes a crystal, sugar crystals look really similar, right? But you can burn sugar crystals at about 100 degrees Celsius, right? You heat them up and they will burn. They will break apart. They will turn into something else, turn into carbon dioxide and water. Salt, if you heat salt up to 100 degrees, is it going to burn and turn into something else? No. You can actually get salt so hot it will melt. You can get molten salt and pour it into a mold and things like that. It's a really strong bond. Ionic compounds make minerals. They make crystals. In other words, they make rocks, big dumb rocks. That's what ionic compounds are. So these are what we call ionic bonds. Form ionic compounds, which are minerals, rocks, crystals. And the thing I mentioned the other day, can everyone put the pencil down for a second? Don't write this because it'll probably just confuse you more. But is unlike a covalent compound where there's like a specific molecule, this just keeps growing. So again, pencils down. You'll have lots of time. Pencils down. Put them down. All right. So if you look here, like you end up with this, where you get a sodium that gives an electron to a chlorine. Then when the next sodium gives its electron away, it might stick here, but it gave it to a chlorine, so that chlorine might stick there. The next sodium that comes around might go there. Its chlorine might go here. The next sodium might go there, and its chlorine will go here. And do you see how this just keeps happening? And of course, I'm drawing it in 2 dimensions, but this actually happens in 3 dimensions, and it just forms a big crystal structure. And it's really interesting because it actually forms a cubic structure in this case because it's a 1-to-1 ratio. And you can see that on a big scale. If you look at salt under a microscope, it's got these cubic crystals. It actually makes pretty like hard-shaped lines. And that's just because that's how this forms as these ions come together, right? So there's no such thing as a single sodium chloride molecule like there is water, right? Ionic compounds form into big crystal structures, big dumb rocks. But the ratio in this case is NaCl, which means 1 sodium for every 1 chlorine. Does that make sense? Great. I've got a sick child who I'm a little worried might come home from school, and I just got a message. So I'm going to break my own rule, and I'm going to quickly check that. And you can all throw things at me and jeer at me and yell at me and tell me I'm a bad person. Okay, good news, child safely at school. Okay, sorry about that. Listen, if any of you has children at home and they're ill one day and you're worried they might have to come home from school, you have my blessing to check your phone. Also, we need to talk if you have school-age children. But that's a different discussion. Nobody in here has school-age children? Okay, good. The math on you guys having like an 8-year-old would be a little weird, you know? You see what I'm saying? Like, just a little weird. Anyway, okay. So, can we try that again? So sodium chloride is what you get when you mix sodium and chlorine. I want you to try this again. I want you to do it. Now, this one might be a little bit trickier. Not super tricky, but a little bit trickier. This one doesn't work as nicely. Magnesium and fluorine. Get on it. 3 minutes and 40 seconds. Starting now. Okay. Focus.
You're actually out of your mind.
Right?
Exactly. Where did you learn to print?
Science room.
Yeah, makes sense. Well, then you just stop. Okay, I know to work our colors, but I also Okay. That's kind of scary. Isn't that illegal? Could sue them.
somebody talk to me. So when oh, hi, wow, Yarsh, go.
You just put 2 fluorines.
Okay, good. But 2 fluorines, and I'm good.
And 1 magnesium.
And 1 magnesium.
Am I actually right?
Yeah, you're beautiful, but I do want to draw it. Sorry for being sassy. I sassily just wrote in words what you told me to do. When I draw magnesium, what's that look like? How many electrons does it have in its valence shell, in its outer shell? It has got 2, or possibly 2, is one of the answers I just heard, which I think is also correct. And when I go to draw fluorine, how many electrons does it have in its valence shell? 7. That was a little bit like, it's got 7. I don't know, that made me a little uncomfortable. But that's okay. Don't let my discomfort get in your way. There we go. So the problem here, of course, is that magnesium can give an electron to fluorine, and that fluorine is now stable, right? It's got a full shell. So we could go over here and we could say, hey, here's fluorine. It's got its now how many electrons? 8. So it's stable. What will its charge be? -1. Excellent. But can I draw the magnesium here yet? Is it stable? No, because it still has another electron. It can't give another one to fluorine because fluorine has already lost it. But like we said, listen, these reactions never happen in a vacuum. You will never be in a situation, I promise, where you are out counting atoms and you go, okay, I've got 1 magnesium atom and 1 fluorine atom and I'm going to put them together. They're too small. You're going to mix a piece of magnesium. We're not going to use fluorine gas because it's deadly and poisonous. But if you were, you take a piece of magnesium and you take some fluorine and you put them together, you have got trillions of magnesium atoms and trillions of fluorine atoms. Does that make sense? If you have the smallest sample ever. So, if the magnesium can't react with just 1 fluorine, it can react with a second one, right? And so we can draw a second fluorine. It will also have 1, 2, 3, 4, 5, 6, 7 electrons, and the magnesium can give its electron to that fluorine, and that means the magnesium now will be stable. It's got an empty shell. And again, like we mentioned, it really obviously has a full valence shell, but its former valence shell has been emptied out. What will its charge be? +2. Why +2? Yeah, it gave 2 electrons away, and positive because if you're giving away negative things, you become positive. Excellent. And then we can draw the other fluorine. Why did I draw the magnesium between the fluorines? Why didn't I draw like the 2 fluorines next to each other and then the magnesium off to the side? Yeah, because the whole point of the ionic bond is that opposite charges attract. So in this orientation, the magnesium is attracting the fluorines, but the fluorines are trying to get away from each other. So it's going to end up in the middle. Something we should think about. If we wrote this out as a reaction, we could say that magnesium reacts with fluorine. And of course, we actually know that when we find fluorine in nature, what's it look like? It always actually comes in pairs, right? Remember that? It's one of our, what do we call those? Diatomic elements. But we end up with something called MgF2, right? The numbers here tell us how many. So when we look at this formula, it tells us that to make magnesium and fluorine into an ionic compound, we need 1 magnesium, but we need how many fluorines? 2. What would this be called? Excellent thinking, but ionic compounds are big dumb rocks. In covalent compounds, we need to use mono, di, tri, all that, because there's different ways to put things together, right? Remember we said that? You can put covalent compounds together however you want. You make anything you want. It's like Lego, right? As long as carbon makes 4 bonds, so we have to say, you can't just say carbon and oxygen, because there's an infinite number of ways to put carbon and oxygen together. Magnesium and fluorine, there's actually 1 way to put them together, and this is it. Because they're big, stupid rocks. This is how they come together. So we actually don't use prefixes. Yep. That would be magnesium chlorine fluoride. And you'll see combinations like that where you can actually mix different ionic crystals together. But in terms of just magnesium and fluorine together, but that's a good question. You absolutely can do that. You can have more than just two species. But we're dealing with what we call binary compounds, so just one of each. But that is a real thing. So this would just be called magnesium fluoride. There is no need for prefixes because there's only one way to put ionic compounds together. No need for prefixes, only one way to put ionic compounds together. Yeah. Mm-hmm. Yeah, so that's an excellent question. When we make the formulas like this, and when we say the names, we always work from the left side of the periodic table to the right. So if we did a more complicated one, if we did sodium and hydrogen and fluorine, we'd actually call it sodium hydrogen fluoride. We work from left to right. And if they're in the same row on the left, you could call it hydrogen sodium fluorate, or you know what I mean? But we always work from left to right, which generally means in a binary compound, you always do the metal and the non-metal. But even when we don't say O2C, we say CO2. And we don't say OH2, we say H2O. Does that make sense? We always work from the left side of the table to the right. There's a few exceptions to that, but as a general rule, just like anything else, we read left to right. So that's the usual order. It wouldn't be wrong to do it the other way, but it would be clumsy. And like people would bully you and laugh at you. And like a last check would see you in the hall and be like, ha, and they'd like beat you up and take your lunch money. And you don't want that, right? No, we don't want that. A lot of people don't know that about a last check. Seems like a real nice guy. Bully. Huge. Takes people's lunch money all the time. Holds them upside down, like shakes them until the coins fall out of their pocket. And he's like, don't tell anyone about this. I've got a reputation to upkeep. And they're like, we won't, we swear. And yeah, it's a whole thing. Vicious guy, that last check. Vicious. No, I could take a last check. And you can tell him I said so, too. I think I could take a last check.
Oh.
Because he's like a nice guy. And I'd be like, a last check, that kid needs math help. And he'd be like, what? Let me help. And I'd be like, bam, right in the back. Oh, I'd get him good. Listen, when you got a good strategy, who needs two? Right? Like, come on. Listen, I know how to win a fight. I got another one to it. See, listen, I don't want any trouble, right? Like any of that, right? Like you gotta catch them unawares. That's all I'm saying. Okay. You start crying, and then when they turn away in disgust, right in the back. Anyway, that's all. Any other questions? See, this is good because I'm teaching you chemistry and life skills. Chemistry, life skills. You get a little bit of both in this class. That's important. And every once in a while, we talk about English. So that's good. And history. See? It's a multi-use classroom, this. We just do a little bit of everything. All right, now. Texas? All right, now, listen. Shh. You can draw it like this all you want. And there's nothing wrong with drawing it like this. This will get annoying if you have to draw a picture every time. But don't let me stop you. Like, that's a good technique. Some of you may have been taught, there's different ways they teach, crisscross method, this or that. I don't tend to like things that seem gimmicky. I'd rather you understand it. If you look here, we needed 2 fluorines because every fluorine can only take 1 electron, but we know magnesium has to give away 2 electrons, right? So, again, there's lots of little math tricks that teachers teach to do this. There's nothing wrong with any of that. I'm not criticizing any previous teacher you had. I'm not criticizing any Khan Academy video you watched or whatever. They're all legitimate. I'll just show you how I keep track of this when I'm figuring out a formula, which at first I would encourage you to actually write down on the page, and eventually you'll probably find that you just do in your head. But my method is this. It's charge balance. It's just the idea that to put 2 things together, the charges have to balance out. So, let's say we're looking at calcium phosphide. Calcium, of course, is Ca, and phosphide means that it is phosphorus, which is P. Okay, here's what I do. I make a little table. I just make a little table like this. And I basically say, okay, if I were drawing this, calcium is going to give away how many electrons? Look at the periodic table. How many electrons is calcium going to give away? 2. So I would say, well, calcium gives up 2 electrons, which means if I had 1 calcium, it would give up a total of 2 electrons. If I had 2 calciums, if I drew a second one on the page, now how many electrons would I have given away? 4. And if I had drawn 3, now I would obviously have, and we won't need to go this far, but let's just, for the sake of argument, if I had 4 of them, I'd have given away 8 electrons. Does that make sense? I'm just saying, I'm not going to sit here and draw 1, 2, 3, 4 calciums with 2 electrons each. I'm not going to bother drawing that. I'm just going to say, if I did draw it, how many electrons would I have? Does that make sense? Okay. What about phosphorus? How many electrons does phosphorus need to gain? Yeah, 1, 2, 3, right? 3 to get a full shell. So I'd do that. I'd say, okay, if I drew 1 phosphorus, it would give away, or it would take 3 electrons. Does that work? Does 1 calcium and 1 phosphorus work if I drew them? No. I'd obviously have to draw another phosphorus. So if I draw the second phosphorus, how many electrons will they be able to take total now? 6. Does that make sense? And now, wait a minute, what do we notice? We found a match, right? Which is, if I have 3 calciums, I'll be able to give away a total of 6 electrons. And if I have 2 phosphoruses, I'll be able to take 6. Does that kind of make sense? So there's no math trick here. Like, you're actually just saying, well, what would it look like if I drew this? And now, like, I'll never do this again, but I could actually draw this quickly. I could say, okay, 3 calciums gives me a charge of plus 6, which should cancel perfectly with 2 phosphoruses, because that will give me a charge of minus 6. Now, the whole point of doing this is not to draw it, but just to show you that it works. If I had 3 calciums with 2 electrons each, and now I just draw 2 phosphoruses with 5 electrons each, because that's how many they have, that's going to work perfectly, because that electron goes there, that electron goes there, that electron goes there. This one goes here, that one goes there, that one goes there. They balance. Does that make sense? Now, the thing is, doing this means that I don't have to draw that and draw arrows and be messy. Now, some of you may be like, yeah, but last year I just learned that you just switch the numbers and it works. Whatever your method is, that's fine. I'm always going to draw this little table, because when we get to more complicated examples, thinking your way through what it actually means, I think, is helpful. Does that make sense? But I'm also not here to tell you what you have to do if you have a system that works. So then, how many calciums do we need? 3. And how many phosphoruses do we need? 2. So Ca3P2 is the chemical formula for the compound calcium, and we don't say phosphoride, we just say phosphide. Good. That's calcium phosphide. Again, if you want to draw the picture, don't let me stop you. If you were taught a different method and it works for you, don't let me stop you. I like this because it's not a trick. We're literally just saying, how many electrons does calcium give up? How many electrons does phosphorus take? So we're not like fooling ourselves into getting the right answer. We're actually talking about the chemistry. Do you want to do one more together? Can we do another one together? Let's go down to barium nitride. Barium and nitride means nitrogen. And boy, if I've drawn this table once, I've drawn it 6,000 times. How many electrons does barium want to give up? 2. So a first barium would give away 2 electrons. A second one would give away a total of 4. If we had 3 of them, we'd be giving away a total of 6 electrons. If we had 4 of them, we'd be giving away a total of 8 electrons. Nitrogen, how many does it want to take? 3. This is annoyingly kind of the exact same example as the last one. That's okay. 1 nitrogen would take how many electrons? So 2 of them would take a total of how many? And what do we notice? Yeah, we found our match, right? That's where it matches up. And that means that how many bariums do we need? 3. And how many nitrogens do we need? 2. Now, an important thing to note. Don't write the charges down, all right? Look at me. Pencils down, put them down, because this always happens. I write the example of like what not to do, and then somebody half paying attention writes it down, and so just pencils down, all right? Ready? It's not this. God, I see this so often, and it makes me want to cry, okay? Because the whole point is, once they're together, the charges cancel out. So once they're stuck together, there isn't a charge, because the bariums are positively charged, the nitrogens are negatively charged, and when you put that all together, what do you end up with? No charge. The charge cancels. They're stable, and they don't have a charge. So the formula here would be what? Ba3N2. Does that feel somewhat okay? All right. I want you to practice the rest of the sheet. And I also want you to practice naming. Naming of these is absolutely trivial because you don't need to worry about prefixes. Again, prefixes aren't for ionic compounds. They are for covalent compounds. So as soon as you see a metal, there's no prefixes. See, like rubidium, oh, that's ionic. No prefixes, no mono, no di, no tri. Right? Strontium, that's a metal. No mono, no di, no tri. Magnesium, that's a metal. It's just going to be, what would this one be? I don't know why I'm picking this one as the first one we do, but okay. What would the name of this be? MgS. Magnesium sulfide. Now, I do want to note something. Lowercase, these aren't people. All right? This isn't your uncle magnesium sulfide. They're just compounds. They're important, but they're not people. All right? Sure, they're important. This is a ruler. My ruler is very important to me. You couldn't beat students without it, but it still doesn't get an uppercase R. The name isn't ruler. I would just like to point out that A, somebody broke the edge off of my thing, which makes me very upset. And then B, they were soldering pipes in here, and they dropped solder down on my thing. It's kind of cool, actually. Yeah.
Oh, it feels weird.
Yeah, that's how they soldered the pipes together. So it dripped down onto here. Did you not do soldering in like grade 9 science? Like soldering
You were my
circuits?
science teacher, so you know.
Did I
Who
teach you
knows
grade
what
9?
we were talking
Did I teach you
about?
grade 9?
No,
I taught you
because
grade
I was
10.
in SSTW.
I taught you grade 10. I taught you grade 10. Oh boy, don't you.
I never did soldering ever.
I love soldering.
Yeah, I've never done soldering because in that class you like.
Okay, so listen. Lowercase, ending change to "ide," and then this is important. What do we not have when we name ionic compounds? Prefixes. All right, now, there's practice here. I'm also going to give you a little bit of online homework practice. Just a little bit, right? Not a ton. Not a ton, but a little bit. All right? In fact, teacher dashboard, grade 11 University Chem, assign homework. Not going to score it, just simple. We want to do how many you get correct. We're going to assign this today. It's going to need to be done by Monday.
Get out. Honestly.
I agree.
I'm gonna sit beside you tomorrow. I mean, not
You're not
tomorrow.
going to sit beside me tomorrow.
I don't want to sit beside you Monday. Can I put this under a microscope? What would you say?
Yeah, go nuts.
Is there actually anything?
It's probably just going to be like.
Okay, so listen. I'm going to assign you as well by Monday, draw some Lewis structures, do a bit of ionic naming, and then just to make sure we don't forget, also to do some covalent naming. These are quick, shouldn't take you long. And there we go. Oh, I need to give it a title. This was less than 1.5, right? Adding. Chloe. Yes, I do. Where's Chloe? Chloe's here. She's in the back.
Maybe she left for
No, Chloe's here. Is Chloe... Did Chloe step out? But she was here today. I'm not going crazy. Okay. She's here.
Perfect.